Group 4 element. Group 4 is a group of elements in the periodic table. It contains the elements titanium, zirconium, hafnium, and Rutherfordium. This group lies in the D block of the periodic table. The group itself has not acquired a trivial name, it belongs to the broader grouping of the transition metals. The three Group 4 elements that occur naturally are titanium, zirconium, and hafnium. The first three members of the group share similar properties, all three are hard refractory metals under standard conditions. However, the fourth element Rutherfordium has been synthesized in the laboratory, none of its isotopes have been found occurring in nature. All isotopes of Rutherfordium are radioactive. So far, no experiments in a supercollider have been conducted to synthesize the next member of the group, Untitled, and it is unlikely that they will be synthesized in the near future. Like other groups, the members of this family show patterns in its electron configuration, especially the outermost shells, resulting in trends in chemical behavior. Most of the chemistry has been observed only for the first three members of the group. The chemistry of Rutherfordium is not very established, and therefore the rest of the section deals only with titanium, zirconium, and hafnium. All the elements of the group are reactive metals with a high melting point. The reactivity is not always obvious due to the rapid formation of a stable oxide layer, which prevents further reactions. The oxides TiO2, ZrO2, and HFO2 are white solids with high melting points and unreactive against most acids. As tetravalent transition metals, all three elements form various inorganic compounds, generally in the oxidation state of +4. For the first three metals, it has been shown that they are resistant to concentrated alkalis, but halogens react with them to form tetrahalides. At higher temperatures, all three metals react with oxygen, nitrogen, carbon, boron, sulfur, and silicon. Because of the lanthanide contraction of the elements in the fifth period, zirconium and hafnium have nearly identical ionic radii. The ionic radius of Zr4+ is 79 picometers and that of Hf4+ is 78 pm. This similarity results in nearly identical chemical behavior and in the formation of similar chemical compounds. The chemistry of hafnium is so similar to that of zirconium that a separation on chemical reactions was not possible. Only the physical properties of the compounds differ. The melting points and boiling points of the compounds and the solubility in solvents are the major differences in the chemistry of these twin elements. Titanium is considerably different from the other two owing to the effects of the lanthanide contraction. The table below is a summary of the key physical properties of the Group 4 elements. The four question-marked values are extrapolated. William Gregor, Franz Joseph Müller and Martin Heinrich Klaproth independently discovered titanium between 1791 and 1795. Klaproth named it for the Titans of Greek mythology. Klaproth also discovered zirconium in the mineral zircon in 1789 and named it after the already known zirconerdi. Hafnium had been predicted by Dmitry Mendeleev in 1869 and Henry Moseley measured in 1914 the effective nuclear charge by X-ray spectroscopy to be 72, placing it between the already known elements lutetium and tantalum. Dirk Koster and George von Hevesy were the first to search for the new element in zirconium ores. Hafnium was discovered by the two in 1923 in Copenhagen, Denmark, validating the original 1869 prediction of Mendeleev. There has been some controversy surrounding the discovery of hafnium and the extent to which Koster and Hevesy were guided by Bohr's prediction that hafnium would be a transition metal rather than a rare earth element. While titanium and zirconium, as relatively abundant elements, were discovered in the late 18th century, it took until 1923 for hafnium to be identified. This was only partly due to hafnium's relative scarcity. The chemical similarity between zirconium and hafnium made a separation difficult and, without knowing what to look for, hafnium was left undiscovered, although all samples of zirconium, and all of its compounds, used by chemists for over 2 centuries contain significant amounts of hafnium. Rutherfordium was reportedly first detected in 1966 at the Joint Institute of Nuclear Research at Dubna. Researchers there bombarded 242Pu with accelerated 2,2Ne ions and separated the reaction products by gradient thermochromatography after conversion to chlorides by interaction with ZrCl4. The production of the metals itself is difficult due to their reactivity. The formation of oxides, nitrides, and carbides must be avoided to yield workable metals. This is normally achieved by the Kroll process. The oxides are reacted with coal and chlorine to form the chlorides. The chlorides of the metals are then reacted with magnesium, yielding magnesium chloride and the metals. Further purification is done by a chemical transport reaction developed by Anton Eduard van Arkel and Jan Hendrik de Boer. In a closed vessel, the metal reacts with iodine at temperatures above 500 degrees C, forming metal iodide. At a tungsten filament of nearly 2000 degrees C, the reverse reaction happens and the iodine and metal are set free. The metal forms a solid coating on the tungsten filament and the iodine can react with additional metal, resulting in a steady turnover. If the abundance of elements in Earth's crust is compared for titanium, zirconium, and hafnium, the abundance decreases with increase of atomic mass. Titanium is the seventh most abundant metal in Earth's crust and has an abundance of 6,320 ppm, while zirconium has an abundance of 162 ppm and hafnium has only an abundance of 3 ppm. All three stable elements occur in heavy mineral sands or deposits, which are placer deposits formed, most usually in beach environments, by concentration due to the specific gravity of the mineral grains of erosion material from mafic and ultramafic rock. The titanium minerals are mostly anatase and rutile, and zirconium occurs in the mineral zircon. Because of the chemical similarity, up to 5% of the zirconium in zircon is replaced by hafnium. The largest producers of the Group 4 elements are Australia, South Africa, and Canada. Titanium metal and its alloys have a wide range of applications, where the corrosion resistance, the heat stability and the low density are of benefit. The foremost use of corrosion-resistant hafnium and zirconium has been in nuclear reactors. Zirconium has a very low and hafnium has a high thermal neutron capture cross-section. Therefore, zirconium is used as cladding of fuel rods in nuclear reactors, while hafnium is used in control rods for nuclear reactors, because each hafnium atom can absorb multiple neutrons. Smaller amounts of hafnium and zirconium are used in superalloys to improve the properties of those alloys. The Group 4 elements are not known to be involved in the biological chemistry of any living systems. They are hard refractory metals with low aqueous solubility and low availability to the biosphere. Titanium is one of the few first-row D-block transition metals with no known biological role. Rutherfordium's radioactivity would make it toxic to living cells. Titanium is non-toxic even in large doses and does not play any natural role inside the human body. Zirconium powder can cause irritation, but only contact with the eyes requires medical attention. OSHA recommendations for zirconium are 5 mg/m3 time weighted average limit and a 10 mg/m3 short-term exposure limit. Only limited data exists on the toxicology of hafnium.